Hey everybody, this is Larry. This is September 9th, the 9th day of the September Leetcode Day Challenge, because that's how you count stuff. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem, largest plus sign. Yeah, remember, join me on Discord, come hang out, 9 days, and we'll do it for the rest of the month and maybe beyond, because I've been on I don't know how long my streak is anymore. It's like 520 days, 530 days, something like that. So I'm gonna do the math from April 1st. Of last year, not a joke, not a April Fool's Day thing. But anyway, so today's problem is largest plus sign. So you're given an integer n plus n grid, some ones, and you find the largest plus. Does it have to be just length 1, or like can it be? I guess my question was that, like, can you be a 2 by 2 by 2, or like a 2 by 2 plus? Seems like that's not the case. Okay, I mean, this seems pretty okay. I think in a dynamic program kind of way, and you know, so let's go over some stuff real quick. So n is less than 500. What mine's that length? What's n again? N by n grid. What are mines? Mines are basically the grids of the ones. Okay. That's a little bit awkward. Like, I thought they were just gonna give us the grid. Okay. Oh, they want to give us just zeros. Okay, I mean that's fine too, but same information. So now you have a 500 by 500 grid. Let's see. I mean, there are a couple of things we can do, right? I think the thing that I'm thinking about, though it may not be the most efficient, but but the same idea, but an optimized version of that is probably gonna be the idea. I think we can just start with just constructing the grid. 500 squares should be fast enough, and as long as we have a 500 square technique, then that should be fast enough, right? Where 500 is the size of one side. So the naive algorithm is just that, okay, you have 500 by 500, so then now we just go up, down, left, right from each cell, each possible one, and then calculate it, right? In the worst case, however, this is going to be 500 cube, because it can go all the way up for each one, and that's going to be too slow. But with some optimization, with some memoization, we can actually do this in n squared time. But and we'll kind of look at this in a sec. Yeah, I mean, I think that should be okay. Let's at least get it started, and if it takes too much room or takes too much time, then we can figure out how to optimize. I think the thing that I always say is that, you know, don't prematurely optimize. That's one. And the other thing is that on Python in Leetcode is a little bit awkward, because in Leetcode specifically, the running time for time limit exceeded is the sum of the test cases, right? So it depends on how many test cases you have. So 500 square, maybe, I mean, it will definitely be good for one test case because you have enough time, but maybe there's like 1,000 test cases, then that's not fast enough. And that constraint, of course, is not given to you in the constraints. So you have to do some guesswork and hoping work and whatever it is that you need to do. But yeah, okay. So let's actually start by creating the grid. I like my n's to be uppercase just for consistency. So let's change that, and then we set everything to 1 times n for so n by n grid of ones, and then now for x, y, and mines, we just set grid of x, y, is equal to 0, right? Okay. And I'm gonna do this recursively, though maybe it's a little bit inefficient in that it does create some additional core stack overhead, but I think that it'll be easier to kind of understand how the problem, so that you can optimize this in the future. But anyway, I'm going to keep it in a way such that it's easier for me to explain and teach, and then we'll see if it's fast enough, and then we'll talk about some things that we can optimize for if it's fast enough, or if it's not fast enough, and then we'll play around, right? So then now we'll just do the naive algorithm, right? So let's do the naive algorithm, which is that for each cell, let's just do if grid of x, y is equal to 1, we do you know, in theory you'll do something like for L is in range of L or something like that, and then, you know, you basically go up, down, left, or check up, down, left, right, and then you kind of just keep going, and then until the first no good, right? So that'll give you the answer for sure. So, you know, you might have something like return best is equal to 0. If this is the case, then we if, let's see, with grid of grid of x, y, I mean, you have to do all 4 directions, right? So something like this, if this is equal to 0, or this is going to be, I mean, you could actually write another for loop. I don't know. Sometimes I go back and forth on whether this is worth another for loop, but you have something like this essentially. Right? And then if this is the case, we break. Otherwise, best is equal to max of best L plus 1, I think. Yeah. And actually, technically, I think you should start here. No, I mean, this should be always be true because of this thing. So yeah, so that's good. Maybe you don't even need the if statement in that case. But let's actually also put in the other test case. I guess the other test case is actually useless. But why do I have invalid syntax? Oh, I missed an or. But I think I also have a mistake here, which is that this goes out of bounds, obviously. And we'll see in a second when we kind of run it. I meant to actually put that in, but yeah. So x plus L is I guess this is very annoying actually, just for learning purposes. So yeah. So anyway, let's pretend this works for now, because we're not going to go over here. But basically, the idea for this is that, you just go kind of like a breadth first search kind of thing, where you go up a step, left, right, up, down a step, and all at the same time, right? If this is out of bounds, or if it is 0, we break. I didn't want to do out of bounds one again, just to be clear, in case you're joining in now for some reason. And I would say that I usually start these live, so if it's a little bit slow, just fast forward or watch it at faster speed. But yeah, so this is going to be work. Let's just say that's going to work, right? However, this is going to be O of n, this is O of n, and this is O of n, and that's going to be O of n cubed, right? So what can we do? Well, we can, for example, we do all the dimensions at the same time, right? So maybe one thing we can do is that we can do one dimension at a time, right? And what I mean by that is checking up independently. For example, you can have something like this, and then this is just, check up. Though technically, yeah, and then you would have to do some additional logic to kind of get the, like maybe up max is equal to 0, and then this is up max is, increased by 1, and then here we check left, or something like that. I don't know. I guess technically left would be minus, but yeah, and then left max, it goes to 1, something like that, right? I'm not going to do the other two because I don't know, I'm lazy, but then at the very end, but this is just for illustration anyway. This is going to be best is equal to best of the min of the up max, left max, right max, oops, and down max, something like that, right? So yeah, so let's just say, add some dot here, do the same with check right and down. So the thing with this now, of course, is that, we didn't change anything. This is exactly the same, which is kind of what we want. So this is n cubed still, so we didn't change anything, just to be clear. Okay, so then what do we want to do next? The thing to take advantage of is noting that you can actually count these backwards, right? So this up max, for example, up max is equal to, if you want to think about this recursively, up max is just equal to 1 plus get up max, naming stuff is tough, of x minus 1 y, right? Something like that. I think maybe I did my here wrong. This actually goes down. You depending on how you want to do it, but that's the idea, right? Yeah. So basically, going up is equal to 1 plus the max of going up of the step that's of the cell that is up, right? And you can do the same for left. Oops. Right now, left max is equal to 1 plus get left max. I guess this is x minus 1. Right max, and I guess I should be consistent and have camel case. Hang on. Oops. 1 plus get right max. X of y plus 1, and then down max is equal to 1 plus get down max of x plus 1 y, right? Let's also correct these. So far still we have not changed anything. It is still n cubed. Let's just say that these are recursive functions. And I guess to be clear, the more clear way maybe, instead of kind of writing it like the way that I did, to be honest, it's just to kind of do this, but for the xy coordinate, right? So then get up max from xy will be equal to 1 plus get up max of x minus 1 to go up, and then y. Assuming, of course, the base condition of if with minds of xy. Oh no, not minds of xy, but with grid of xy, it is 1. Well, if this is 0, we just return 0, because that means that that means that you can't go up anymore, right? So that's basically the idea. And then here we can do the same thing for left. And this is, of course, a little bit awkward in that we're writing 4 functions, of course, 1 for each direction. I'm not going to go over the technique now, but you can actually combine them into one more generic function if you like. But and there's a couple of ways I can do that, but I'm not going to do that for this video just because I'm trying to keep it for beginners to be this technique of basically now we what I call writing a loop with tail recursion instead, right? Of course we have 4 of them. And I actually messed up here, so I forgot to check for bounds again. So I will have to add that in. Get down max of x plus 1 y, and this is of course so this is just we can actually use a decorator to if you're familiar with Python, we can actually have a decorator that checks the inputs. Not going to do that for now because decorator syntax is very confusing for the beginners and me to be honest as well. No, I mean it's not that bad, but it is hard to kind of understand for beginners, so I'm not going to do that with respect to decorators. But I know if you're a Python enthusiast and specialist, you'll be like, oh, why didn't you just use a decorator? I know. I just wanted to kind of get this on. Anyway, let's run this code real quick. I think it should run unless I have an additional typo somewhere. It might be slow, but it should run. Okay, well. That was up dog. Oh wait, I messed up the statement. Let's see if this is if this is not true, then we return 0. Whoops. I was talking about doing it about decorators, then I got distracted and forgot. Yeah, if this is not true, or this actually messed up again. Basically, if it's out of bounds or there are minds in it, then we can just do this, right? I will also say that you may also notice that because we only use the grid to check this and this, we actually could also have put all the minds in a set. I know, I just kind of try to keep it simple. But yeah, so you can see that this works. The only issue is that it's still n squared, right? Say. So this should probably time out. I mean, it might actually be fast enough, but given enough test cases, it would not be fast enough. But I don't know. Yeah, it is too slow. So basically, the other thing to notice is that now that we put in tail recursion, notice that these functions have a property that makes it memorizable. And what is that property? That property is that for every single input we get the same output, right? Because that doesn't change any time. So for every same input we get the same output, and that same output is yeah, and that's the same output is deterministic, and there are no side effects. So you can you can just memorize is what I would say. And this part is a little bit more annoying to write as well because I'm trying to do it for learning reasons. But yeah, so then here you can just write up. Let's just say like 1 times n up cache maybe. You can write this in a few different ways. I've already spent 15 minutes on this video, and I'm a little bit tired because it is very late where I am. So otherwise I would maybe even go over this in more detail, but as a result, this is just easy, right? So here I just choose a value that is impossible. I don't usually do it this way, to be honest, especially for learning. I think the way that I usually teach is having two different storage, one for whether the cache exists, and then another one for the value. I'm just being a little bit lazy today, so excuse me, but it's a little bit late. There's a lot of copy and pasting the way that I'm doing it, and as as some of you might notice, I'm doing this for learning purposes or teaching purposes more particularly. Otherwise, yeah, I would not probably have done it. I would probably do this. You can, yeah, as an upsolve, you can probably do this, all these functions in maybe 6-7 lines of code, maybe a little bit more, maybe 10 lines of code at most. See if you can challenge yourself to do that. But yeah, otherwise, yeah. Or you can write this in another way, which is that if this is -1, we update the cache, and then we just return this. Yeah, so that's basically the idea for the up cache. And of course, we do it for the other ones as well. So this is gonna take some time. Pretend this is a montage. You could fast forward, play some music in the background, some copyright music that I'm not gonna play, and pretend that this is a montage. Like, and then that'll keep it fun. But anyway, you see what I'm trying to do here. This is just caching. Yeah. And you could cache to 0 as well, but that's a little bit more awkward, at least in this case. And it doesn't generally matter because that's, it's an all of one check, and I wrote the wrong one. So barring typos, that's pretty much all we have for this one, though. I might need to. I'm gonna go over the complexity really quick, but even then, we're pretty much the way there. Let's run it again. Yeah, and you can see that this is much faster. Still, a second is a little bit slow, a little bit discerning, but it should. Hopefully, it gets us fast enough. If not, we have to do a slight more optimization. I mean, I did this kind of for visualization and for teaching, but yeah. So let's give it a quick submit, and hopefully this is fast enough. If not, then I'm just gonna be sad because that should be fast enough. Dong dong dong. Oh no, we're gonna be too slow. Too slow. That's sad. I mean, and this is only sad because as we kind of demonstrate, for every input, we are going to be fast enough, but it just depends on how many test cases they have for us. Only 56, but I guess if a couple is longer than that, this is already too long. Yeah. Yeah. I think. How do I want to do it? So the first thing that you get. So let me go over the complexity real quick, just for learning at home. And all 4 of these functions are the same, so I'm just gonna go over one of them. It's just in a different direction. But basically, you know, you look at every how many possible inputs there are, right? So x can go from 0 to n, y can go from 0 to n. So that means that this is O of n squared input. Each input takes O of 1 time, and each input takes O of 1 space. So in total, it's gonna be n squared time, n squared space, right? And then times 4 because you have 4 of these, but that's still the same big O. And of course that makes each of these function calls O of 1. So combine this with the O n squared loop. In total, it's going to be n squared plus n squared, which means O of n squared. So the n squared is going to be fast enough, but I think we just have to do some fixed constant speed up things to kind of make this one fast enough. We do pass all the test cases. It's just, I guess the recursion is sometimes too slow, and it is what it is. But yeah, and you can do that by instead of doing tail recursion, we can do it with an explicit stack, I suppose. But yeah, I mean, I think we can just write it, but basically with the same idea, right? We just basically, we have this idea of a cache, and then we keep going up until we can't, and then we come back down. So let's do it that way. But here we just unroll the loops. So here we go. Okay, how do I want to write this? So then we just go for L in range of 1 to n, say. It doesn't really matter because we break earlier, but this is just annoying to write. Let me think about this for a second. Hang on. I mean, there are a couple of ways to do this as well. There's also you can do it backwards if you're really smart, with respect to like it's almost like pre-processing the prefix sum. So here what you can do, and I think that's what I'm going to do because I'm too lazy to kind of make sure all the edge cases work for what I'm doing. But the idea is that, okay, instead of counting from the ones, we count backwards from either the edge or the zeros and then pre-calculate everything, right? And the way that you can do that is just by one at a time. This is slightly messy as well, but we'll do it. So yeah, so yeah, for x is in range of n, for y is in range of n. Then here now we start at x, y, and then go down, right? Or go, yeah, we start at x, y, and then we go down. Going down meaning x plus 1, and then x plus 1 would depend on the ends on x, right? So here we actually have to rewrite the loops a little bit, at least the way that I like it. Just to, I mean, it's actually for this problem, I don't think it matters, but it does come into play in other things. Actually, and then here our base case would be 0 because that's the longest length, assuming that it is whatever. Is 0 good enough? Ugh. Yeah, let's just say it is, right? And then here we just have to start at this is actually yucky as well, but yeah, now we check to see if there's 0th row. If this is equal to 1, then this is just basically the base case, right? This is going to be 1, else this is equal to 0. So I guess you can actually rewrite this as up cache of 0, y is equal to grid of 0, y, right? So this starts up this first row, and then now for every row we look at the previous row. So then now we can do x, well, let's just start at 1. So then now x of y is equal to up cache of x minus 1y, right? So this is now just calculate the up backwards. Well, no, sorry, this is wrong. So if grid of xy is equal to 1, then we add the previous row. Else, then this is just 0, right? Because this is 0 because now you don't have the longest streak going. Basically, you're just doing streaks backwards. Okay, and then now this is going to be up. What up, cache? Get it? Okay, fine. But yeah, now we do it backwards for the other ones as well. So here we look at the last So n minus 1 y is equal to grid of n minus 1 y. And then this is also kind of just annoying, to be frank, but yeah. But this is basically the same thing as what we had before. And to be frank, this is also pretty much exactly what we had before anyway. Except for that this is now kind of bottoms up, if you want to play with those terms. Was hoping to go sleep a little bit earlier, but left, right, okay, yeah. I think by default it should be 0 anyway, so, but always good to initialize. But yeah, so hopefully this makes sense what I'm doing right now, but this is actually not a hard problem, but I think I chose the teaching route, but now it's causing me a lot of time. And also, like I said earlier, a lot of why this is a little bit silly, is because we don't know the number of test cases. For each individual test cases, this should be fast enough. Let's run this real quick. So before it was at like 947. Let's see how hopefully this speeds it up by significantly. Oh, whoops, I forgot to update this part. But this is just up cache of xy, left cache of xy, right cache of xy, down cache of xy. Oh, well, I mean, on a good note, this is faster, but on a bad worse note, it is the wrong answer. And I think I just forgot to add a +1. Yeah, because I think I assumed that this already had 1, because usually I prefill it with stuff in the grid, but we don't do that here, so I think I just forgot to do a +1. Should be okay though. Now let's see if this is fast enough. Oh yeah, oh, it's way faster. Why was it not as, I mean, why does it fluctuate so much? Let me take a run again. Yeah, okay, I don't know. But yeah, you can see that this is 3 times faster, so let's give it a submit and hope this is good. Oh, maybe because it just errors. I don't know. It's a little bit weird. But yeah, this should be at least 3 times faster, so we'll see. Yeah, so this should be good enough. Let's actually, I don't usually take a look at timing, but let's at least for this one take a look at this real quick. And it takes 3 seconds, so I think actually our original solution was way close to being AC, but apparently not that, just slightly off. So yeah, and there's still optimizations that you can make, but I'm gonna stop here. And here, I think the complexity, I'll go over it again, but it should be more straightforward in that, this is n squared, this is n squared, this is n squared, this is n squared. That's obvious, hopefully. This is also n squared, so everything, this is going to be n squared times n squared space. I think one more optimization that you can do is noting that, I don't know if this is, not sure that this is going to be faster though, to be honest. It just saves this n squared, but you can actually put mines in a set. It depends on the number of mines you have, and 5,000 is actually a very sparse table that we have, and as a result, you can actually put in a set to do lookups. I don't know if that's going to be that much faster. It really depends on the input size, or the basically the properties of what input they give you. So give it a try. Let me know what you think. Let me know how that works out. Yeah. That's all I have with this one. Let me know what you think. Took a long while to this one, but hope that's okay. Stay good. Hope that you're learning from kind of all these routes that I took with this one. Anyway, that's all I have. Stay good, stay healthy, to good mental health. I'll see you tomorrow. See you later, and goodbye.